today I want to discuss some theorem, and I want to prove some theorems. Okay, so let's start. Example. Example P odd in. So friends, I have already discussed what is the partitions. So friends, odd is meaning of the odd means partition odd partition in. The number of partition only odd parts. This is the meaning. The number of partition only odd parts. So friends, we discuss generating functions P and Q. Q is any number. This formula is 1 divided by 1 minus Q into 1 divided by 1 minus Q square into 1 minus Q cube into 1 divided by 1 minus Q to the power 4 into 1 divided by 1 minus Q to the power 5 up to infinity. So friends, whatever I have told in previous class that this portion is part 1, and this portion is called part 2. This is part 3. This is part 4. This is part 5. So friends, P odd Q. P odd Q means only odd part. I shall take only odd part. Like part 1, part 3 is odd, part 1 is also odd number, part 5 is also odd number. So I shall take it 1 divided by 1 minus Q into 1 divided by 1 minus Q cube into 1 divided by 1 minus Q to the power 5 into up to up to infinity. So it can be written this way: m equals to 1 to infinity 1 by 1 minus Q into 2m minus 1. This is the formula. So friends, P odd Q we have learned. P odd Q means 1 by 1 1 by 1 minus q to the power 2m minus 1. Now, then furthermore, it is similarly follows that the number of partitions into even parts is going. So friends, p even number q, it can be written this way: 1 by 1 minus q square into 1 minus q to the power 4 into 1 minus q to the power 6 into up to infinity. It can be written this way, friends: m equals to 1 to infinity 1 divided by 1 minus q to the power 2m. I hope I can clear this portion, friends, because even part I have to take. I have to take even part. Part 4, this is the part 4, part 2, just multiply in here. I just multiply. This is the part 2, this is part 3. Sorry, this is not part 3, part 3 is this is part 3 is this part is part 3. This part is part 4. This is part 6 also in here. So friends, this is the total way. Part 4 is also even number, because this is even number, so that's why I multiply even number, even parts. So this is the main I hope that I can clear, and this is my formula: 1 by summation 1 by 1 minus q to the power 2m, and so on. Now friends, I want to discuss another example. This is the p even, whatever I discussed, p odd q, partition odd q, p even q. Now I discuss p distinct q, p distinct q. So friends, it is discussions p distinct n. Example, this is another example. Let's see what is the meaning of the number of partition the number of partition with respect to distinct parts So friends, p p q pq is equal to one plus q 1 plus q generating function can be written this way: p plus q plus q square plus q cube plus up to infinity. I just explain this portion. I just break these portions, friends. 1 minus 1 by q, 1 minus 1 by q, this way. I can write this way. So into 1 plus q square plus q to the power 4 plus q to the power 6 plus up to infinity, 1 minus 1 by q square. And another way is 1 plus q cube plus, I just discussed generating functions, q to the power 6 plus q to the power 9 up to infinity. And another, this portion is formula is 1 plus q to the power 4 plus q to the power 8 plus up to infinity. So friends, up to and so on, and is going to so on. Now we discuss number 1. Number 1, these portions. This portions is order 0 part equals to 1, and these portions, this portion is 1 part equals to 1. This portion is two part equals to 1. 2 part equals to 1 partition. So 1 partitions, and up to, and this portion is 3 part, partition 1 for partition 1, and so on. And this portion in here 0 part equals to 1, in here 1 part equals to 2, 0 part equals to, in here, sorry, this is the 0 part equals to 2, and this portion is 2 part equals to 2, and this is 3 part equals to, this portion is 3 part equals to So friends, my discussion is distinct part. I try to explain these portions. What is the distinct part? And 3 part equals to 2. Now let's move when we discuss this portion, then it is 0 part equals to 3, 1 part equals to 3, one part equals to 3, and 2 part equals to 3, and so on. In here also, friends, you see the partitions theorem. Here we see 0 part equals to 4, 1 part equals to 4, and so on. So friends, I think that I can clear this concept. Now let's move. So friends, whatever you notice that each one of these controls the number of parts. And distinct part is there are 0 and 1 of each part. So friends, whatever we see if we observe this series, so we see the distinct part is there are 0 or 1 or 1 of each part. This is the distinct part, friends. Now let's try to give one revisions. So recall what is the partitions formula. Lambda equals to lambda 1 comma lambda 2 up to lambda k with respect to number 1 conditions is lambda 1 plus lambda 2 plus up to lambda k equals to n, and number 2 is lambda 1 greater than equals to lambda 2 greater than equals to lambda up to lambda k, means this function is decreasing functions, and less than equals to 1. So this is the decreasing way. Lambda 1 greater than equals to lambda 2 and lambda k and up to lambda k. So Pn, the number of partition of lambda, Pn is called the number of partition of lambda and PQ is equal to summation n equals to 0 to infinity Pn q to the power n equals to this way, m equals to 1 to infinity 1 divided by 1 minus q to the power m. This is the formula. Now I just recall this formula because this is very helpful. So friends, P distant Q, distinct Q. So friends, whatever we see that 0 or 1 of each part. 0 or each part is I have to take these portions. I will take these portions 0 and 1 plus q square and 1 plus q cube. This portion I shall take. So my solutions should. So friends, whatever I get this way. I also mentioned that how do I get this is I just recall this formula because we use this generating function formula. This is my generating function formula. Generating function formula. So P distinct Q is equal to 1 plus Q into 1 plus Q square into 1 plus Q cube up to so on. Is equal to summation m equals to 1 to infinity 1 plus q to the power m. Let's move another chapter, another examples. Next example is our next example is PRN equals to the number of partitions of n where each part is repeated. Each part is repeated at least 2 times. So friends, whatever you see, PQ can be written this way. We know the generating functions. I apply this formula, friends. Everywhere you remember this formula is very important. these generating functions I will use. So I get this way 1 plus q square plus root up to infinity into 1 plus q square plus q to the power 4 plus up to and so on, and 1 plus q cube plus q to the power 6 plus and dot dot up to so on, and it's going on up to infinity. And it can be written this way. Now whatever you see, the number of partition of n where each part is repeated, at least 2 times. So friends, we see that this part is distinct. 1 plus q is distinct part, 1 plus q square is also a distinct part, and 1 plus q cube is only distinct part. So we shall take this portion q square plus q to the power q cube plus q to the power 4, because at least 2 times. You see that at least 2 times. So friends, you see these portions is whatever I discuss. This is one part, but 2 times. Sorry, this 2 part. This is 2 part into 1 time. This is 2 part. This is 2 part 1 time. This is 2 times. Sorry. This is 2 time. This is 2 time is equal to 1 part. Another is in here q cube. This is the 3 time. When it is the q cube, then it is 3 time into 1 part. Similarly, here this is 2 time equals to 2 part. Means in here also this portion must remember, in here also I just say that it is also time 3 time into 1 part, 1 partitions. This is 3 time, 2 time, and equals to 1 partitions. One time equals to 2 partitions. So friends, I hope I can clear. So 2 time into 1 part. This is the at least 2 time, means at least means 2 time and more than 2 time, but not less than 2 time. Means it should be 2, 3. What is the meaning of at least? At least 2. At least 2 means it may be 2, 3, 4 up to infinity, but not, it is, this value will not be 0 and 1. It is not 0, 1, but less than 2. So friends, this is the main up to infinity in here, and here I shall get q to the power 4 plus up to q to the power 6, q to the power 8 up to this is infinity, q to the power yes, it is the, after that it may be q to the power 6, q to the power 6, q to the power 9 up to infinity, and so on. So it can be written this way: q square divide by 1 minus q into q to the power 4 up to 1 minus q square into q to the power 6 divide by 1 minus q cube, and so on. And so on. So it can be written this way: summation m equals to 1 to infinity q to the power 2m divide by 1 minus q to the power m. So friends, I hope that I can clear. Now I will discuss one theorem. I shall go to the theorem. The number of partitions. The number of partitions of n the number of partitions of n into odd parts equal the number of partition partitions of n into distinct points. So now let's start proof. So whatever we see that the number of partitions of n into odd parts, number of partition of n into distinct parts. So friends, now we recall the formula. We recall the formula. What is our formula, friends? I prove this formula that P odd Q equals to summation m equals to 1 to infinity 1 divided by 1 minus q to the power 2m minus 1. And P distinct part of Q summation m equals to 1 to infinity 1 minus, sorry, not 1 minus, 1 plus q to the power k. This is our formula. This formula I will apply. I shall apply this formula. You will see that. And P distinct P odd Q also I have already told. So let's try to prove this formula. P distinct Q equals to 1 plus Q into 1 plus Q square up to 1 plus Q to the power K. Then we can write this way: 1 plus Q into 1 minus Q multiply 1 minus Q, 1 plus Q square into 1 minus Q square divided by 1 minus Q square up to 1 plus Q to the power K into 1 minus Q to the power K divided by 1 minus Q to the power K. Just multiplying. And whatever I get 1 minus Q square divided by 1 minus Q into 1 minus Q to the power 4 divided by 1 minus Q square into 1 minus Q to the power 6 divided by 1 minus Q cube up to this way. up to and go and so on infinity. So friends, we can write this way, and now we just cut this portion 1 minus q square, 1 minus q to the power 1 minus q square, 1 minus q to the power 4. You can get also in here 1 minus q to the power 4 divided by 1 minus q to the power 8. And these portions also cut, this portion is also cut, and these portions is also cut. And whatever I get, friends, I get 1 divided by 1 minus q into 1 minus q cube into 1 minus q to the power 5 up to infinity. So friends, it can be written this way: m equals to 1 to infinity 1 by 1 minus q to the power 2m minus 1. This portion is called p odd n, odd q. Thanks. So we will start to discuss another theorem, friends. Theorem: the number of partitions of n into parts not divisible by 3 into parts not divisible by 3 equals to number of partitions of n parts repeated at most 1. Repeated at most 1. So friends, at most 1 means it is 0 or 1, not more than 1, at most 1. So let's start to discuss. So let's compare that the last one, so that was odd parts, so we can reinventions odd parts as parts not divisible by 2, and then we had distinct parts, so that like parts repeated at most 0 times, at most 0 times. So in other words, no repetition at all. Something can only happen once, but if it's repeated at most once, then something can happen twice. So we are going to do this just as we did the last one, the generating functions, but we are going to derive the generating functions during the proof. What is the how to prove this? Proof is p r q is equal to 1 plus q plus q square, 1 plus q square plus q to the power 4, and so on. 1 plus q cube plus q to the power 6 and up to so on. So p r q, it can be written this way also, that p r q 1 plus q plus q square into 1 minus q divided by 1 minus q and 1 plus q square plus q to the power 4 divided by 1 minus q square into 1 minus q square up to infinity. Equals to 1 minus q cube into 1 minus q to the power 6 into 1 minus q to the power 9 divided by up to dot dot up to infinity and 1 minus q 1 minus q square 1 minus q cube up to infinity. So friends, whatever we see that these portions already cut. 1 minus q cube 1 minus q to the power 6 1 minus q to the power 9 dot, dot. So whatever we see that this portion can be written this way: m equals to 0 to infinity 1 by 1 minus q to the power 3m plus 1 1 minus q to the power 3m plus 2 equals to p 3q p3q. That I proved that divisible by 3, not divisible by the number of partitions of n into parts, not divisible by 3. So friends, I have already told that even and odd, this is same type but it is divisible by 3. So I proved this theorem. Next friends, I am going to discuss another theorem. I am going to discuss another theorem, Rogers-Ramanujan. The number of Ramanujan identities, the number of partition of n into parts of the form parts of the form 5k plus 1 and 5k plus 4 equals the number of partitions equals the number of partition of n whose consecutive parts differ by 2. So friends, let's start to discuss one example. 4. Let n equals to 9. N equals to 9. Parts of the form 5k plus 1 or 5k plus 4 differ by at least 2. Now 5k plus 4, it is also 9. 9 is 5k plus 1 where k equals to 1, then it can be written as 9. Another is 6 plus 1 plus 1 plus 1 where 6 is also 5k plus 1 form. I hope I can clear this concept. And another formula is 4 plus 1 plus 1 plus 1 plus 1 plus 1. So friends, 4 is also k equals to 0. Then 4 is also 5k plus 4. 5k plus 4 way. And another is 4 plus 4. 4 plus 4 plus 1. Another is 1 plus 1 plus 1. Total up to plus 1. 9 term. Up to 9 term. And differ by at least 2. The first number is 9. Second number is 8 plus 1. 7 plus 2. 6 plus 3. And 5 plus 3 plus 1. Divide. So total is 5. And you will get 1, 2, 3, 4, 5. So total is 5. So we see that this theorem is correct. Now friends, it can be proved also by generating functions.